Hello everyone, welcome to MLAS100, Learning Activity 13, where we're going to jump into the Fall 2022 update for architectural derivatives for artificial intelligence. So first up, let's talk through what we're going to be focused on for this Fall 2022 update, and that is going to be diving into deep learning architectures. So we're going to be spending a bit of time throughout this whole lecture talking about what is deep learning, how does that relate to other types of machine learning. We'll also talk about the different architectures as it relates to deep learning architectures. We'll have a little bit of a TensorFlow lab exercise, which is kind of cool as it's specific to deep learning, and then we'll wrap up with a conversation around short conversation around Free Guy, the movie. So let's start with deep learning here. Deep learning is a subset of machine learning. It's not something that is separate and apart. It is part of machine learning, and it is therefore part of the artificial intelligence domain. Deep learning specifically doesn't have anything to do with doing machine learning better. It's just a different style. It's a different set of class of actually algorithms. And it's a different way of looking at things. So deep learning specifically has to do with neural networks, or specifically artificial neural networks. So what does that mean? Neural networks have their historically are inspired by biological neural networks, or are neurons, so to speak, biological neurons. And on the left is a representation of what that looks like, and on the right is what that looks like from a computational perspective. I guess technically both would be computational, but I guess more specifically on the right, that would be a diagram of what a neural network looks like when we construct it in the machine learning world. So an artificial neural network versus a biological neural network is what we're differentiating here. They both have inputs. They both have outputs. How they handle their connectivity in the middle is still under research. There's different ways to handle that. But to a large extent, the reference to deep learning actually has to do with those blue dots, those hidden units. And that's what we refer to as deep. So a simple neural network will have one hidden layer. It won't have too much to work off of, and that's really typically not a deep learning network. Whereas in this particular case, I've got I've got four hidden layers within this neural network as an example here. And this would be considered a deep learning network, or a deep neural network, a DNN. And we'll chat through what this looks like. But deep learning has actually been around for a long time. It just was under a different name. Deep learning is just a new branding for something that's existed for 70 years. So let's talk about a little bit about the origins. So deep learning, here's a very simple one. On the right, just a depiction of just a high level. You've got an input, you've got a hidden layer, and an output. And this is the quintessential, mechanics, rather, the quintessential architecture of what a deep learning framework looks like. So this is an artificial neural network. And again, based on, inspired by biological neurons, that is essentially what a neural network is. So they have been around. We've called them this for a better part of 70 years. Neural networks were first proposed back in 1944, and you can see here it was out of the University of Chicago, where it was originally conceived, and then those researchers went to MIT and started what was what's considered the first cognitive science department. So it went through quite a bit of MIT did a lot of work on the original underpinnings of artificial intelligence. And there was actually another one that had popped up in the 40s also that we're going to be covering, which is cybernetic sciences. Both artificial, I would say rather, both artificial intelligence and cybernetic science has come out of what's called complexity science. And there's a lot of historical precedents where they both collaborated back in the 40s and 50s on a very similar path. Cybernetics in one vein and artificial intelligence in another. They eventually diverged pretty, I would say, pretty dramatically. The two disciplines diverged back in the 50s and made a really big split back in the 60s. And to this day, they're very much in two different distinct areas. But they are kind of to a certain extent coming back full circle, so to speak. Artificial intelligence more popular than cybernetics, but as Internet of Things starts to pick up, as wearables and integration and technological integration picks up, artificial intelligence has been getting a lot of press lately, but cybernetics is not far behind, just based on how well the hardware and then of course the artificial intelligence as it relates to that matures. So both of those are going to be one so much more now, one is coming up down the road. Going forward here, so here's the concept of what makes them deep. This is on the right is an example of a deep learning network, neural network that was used for drug discovery. And in this case, it's they've got 1, 2, 3, 4, 5 hidden layers with 6 input parameters and then 2 output parameters. In this case, it's fairly large. They've got 6 neurons, 100, 500, 250. So each one of these, this creates a fairly decent neural network, and actually something that we'll be able to test here with our little Tensorflow playground lab time a little bit later in this session. But this is why we call them deep, because of the hidden layers. It's very complicated to tease out what's going on within a neural network, and oftentimes these neural networks get so big for research purposes that the researchers themselves they're not sure exactly how a neural network is doing what it's doing to come out with the output that it does. Sometimes and oftentimes you'll hear deep learning models referred to as black box models, and this is also something that we'll talk about in cybernetics, because there is a crossover there between cybernetics and artificial intelligence. But again, I mentioned that already, but we'll cover that more actually in a few weeks. We're almost wrapped up with this one. MLAS100 is coming up here pretty soon, so this will be it's a good time to start introducing these concepts. Okay, so you're probably wondering, like, how does a neural network work in the first place? So here's a simple one that I pulled from Towards Data Science. It's a pretty straightforward neural network. It's got one hidden layer, and it's got 3 nodes in that hidden layer. In this case, I've got lot size, bedrooms, and average family income as input parameters, and then I have a house price as an output layer, or my output parameter here. So nodes nodes operate off of what's called activation functions. So these activation functions are very much like similar to an activation potential in a biological world, except in a neural network, an artificial neural network, the activation function is a mathematical function. So in this case, I can actually have multiple different styles of it. It's mostly algebra. These activation functions in a neural network primarily runs off of these, either a linear function or a logistic sigmoid, a rectified linear unit, or a hyperbolic tangent. Those are the 4 main ones. And the nodes, and as you're going to see in the lab, will actually be able to see that the activation functions as it relates to the output and what you're trying to do is very, very important, because some mathematical algorithms, it doesn't matter how many you throw at it, will never be able to figure out what it is, whether it's a classification or whether it's a prediction exercise. Will never be able to do what it is you're doing if you're using the wrong activation functions. And in this case, we'll see this in the lab here in a minute, once we get through this. But not only does the activation function itself have importance, but the actual architecture of the neural network itself is very important. So they both together make a big difference as it relates to what it is that you're trying to accomplish. So you have a couple. We won't be able to do all these in the TensorFlow playground. Like for example, a Boltzmann machine. I don't think we're going to be able to set up a Boltzmann machine in our setup, or a neural Turing machine. But in our playground, we'll be able to quickly set up a deep feed forward. We could actually set up a deep convolutional and a deconvolutional network pretty easily. We're actually playing around with the perceptrons, all those nodes in the middle. We're playing around with them a little bit to make this work, but you'll see that the architecture that we approximate using TensorFlow, the playground anyway, is going to give us does make a big difference. So we'll explore each one of a couple, rather, not each one of these. Now, this is not a comprehensive list. There are many more. There's so many different examples of this. If you type in types of neural networks into Google, you're going to find so many different styles. This is just a simplified one, just for educational purposes. There's diagrams that illustrate a good 30-40 of them right out of the gate, so you definitely have a much more rich set of neural network architectures out there. But this is a good start. Okay, so TensorFlow. So let's jump out to, I'm going to bring up TensorFlow here. And let's go ahead and, so what you want to do is playground.tensorflow.org. And let's do Google. And let's just do Google. And let's bring this over here. Hopefully this doesn't give us too much issue. All right. Okay, here we go. So my computer's running a bit slow, but I think we should still be able to do this. So what you want to do is playground.tensorflow.org, and that's what we're looking for. All right. Okay. So here's a simple exercise here that we can run. This is something I want everyone to spend some time with. I'm going to run through 2 different exercises, and then I'm going to let you try to do the spiral one at your own pace. But I do want you to attempt to do this with the spiral. So I'm going to do this one here. So this is just to kind of explain. We won't be able to cover everything, but this is a simple. This has 2 hidden layers. I've got 4 neurons right here, and then I've got 2 neurons over here. And I'm doing I'm going to do a simple. I'm going to switch this to a linear activation. Remember those activation nodes. Now this is going to run off of linear algebra. So think y equals to mx plus b. It's the same thing. But I'm going to do instead of prediction, which is regression, that would be for prediction or predictive purposes. We're going to do this for classification. And what that means is we're going to create a neural network that is going to be trained to identify the blue dots and then identify the orange dots. So we're gonna I made this minor adjustment to a linear activation method for a classification problem. And what you'll do is you're gonna push play, and then it's gonna slowly try to make something happen here, and we'll see if anything does happen. And it doesn't look like anything's going to happen here. I'm not seeing any type of change or adjustment in the output here. So then I'm going to stop, and I'm going to switch this to Sigmoid. I'm just going to roll up and roll through these. So Sigmoid, and then I'm going to push play, and then we'll see what Sigmoid does. So I'm not really seeing anything happen on the Sigmoid front either. So our activation method using a Sigmoid function isn't working. It's really not doing much. And now I'm going to switch this over to a hyperbolic tangent, and let's see what this does. So I'm going to run this as a hyperbolic tangent. Now we got some stuff happening. Now that looks pretty good. So over here, it didn't take long. It literally went through probably less than, if I reset this, let's see, I want to say that happened in probably less than 100. Yeah, right at the 50 mark. 50 epochs. Yeah. So that's essentially, it figured out and classified all the blue properly and all the orange properly, and any more generations of this isn't going to change anything. But what you can see here through this process is through 4 neurons and 2 neurons, we were able to do able to use a hyperbolic tangent as an activation function, and that was the one that worked. Sigmoid didn't work and linear didn't work. So the activation function actually makes a big difference in terms of its ability, in this case, to do a classification. Now, if I run this tangent, hyperbolic tangent, using the same architecture on a different classification, now I've got quadrants. I got two orange quadrants and then 2 blue quadrants, and I'm going to run this now on that and see what happens using the tangent function. And it's not bad. Tangent does pretty good. In less than 100, it was able to do this. Let's see if we can actually, let's start over again. We'll do this with linear and see if linear can be done, if linear is able to do it. So not much is happening on the linear. It's not looking too good for linear. So we'll run Sigmoid. See if Sigmoid isn't doing anything either. So we know the tangent. Let's use the rectifier, and we're having trouble with that one too. So it looks like pretty powerful so far. Oops, that the hyperbolic tangent so far is able to do what we want to do here. Yeah, that looks pretty good. Gives us it does what it needs to do there. Now, let's play with this a little bit. Now that we've gone through the activation layers, let's go and talk through our different. So we had over here different networks. So if we have let's say a deconvolutional neural network in style. Now there's a couple things missing here, but we can actually create something similar to this in style. So let's go back here, and what we can do is, we know that what we need for this is a couple more hidden layers. I think that's fine. Let's drop this. We can drop the number here, and we can add one here. We can add that, and then okay. So now that's kind of in the same style of what you saw over here in terms of the deconvolutional neural network, in terms of it fanning out from the input features. And so if we rerun this, will we still get the same thing? Will the tangent be able to? Still works, a little bit different. It changed blue on the bridge versus orange on the bridge. Now let's see if this actually makes a linear function work. It won't. See, So the architecture has, the architecture, even though we've changed the architecture, the activation function has no effect on our ability to classify the blue dots versus the orange dots in this example. Now let's go over to, let's switch over to a different classification pattern and see if there's anything that can be picked up. And it doesn't look like it. Now, there are different features we can feed this over here that you can play with, that give that provide some additional feature input before going into the neural network. I'll let you play around with these, but one last thing I want to show, because you can actually